Welcome to a quick review of eigenvectors and values. I thought this would be instructive, so let's go ahead and do a quick review of these. So suppose we had two vectors. Let's call these vector x. This vector has an entries 1 and 0, and we also have another vector y, and this has entries 0 and 1, and yet another vector t, which has entries 1 and 1. These vectors may geometrically be represented as I have drawn here. So according to this, notice here, our x coordinate is 1 and our y coordinate is 0. If we were to draw such a line, it would look like this red line. So geometrically, vector x bar is represented by this red line. And the same goes for y bar. Its x entry, its x coordinate is 0 and its y coordinate is 1. So if we were to draw a line represented by this vector, it would be represented by this blue line. I have to say that this has not been drawn to scale, so don't pay attention to the scale. This is just a schematic. Now what about vector t bar? Vector t bar extends 1 unit along the x direction and also extends 1 unit along the y direction. So that vector is represented by this line over here. So that's vector t. That's a geometric representation of these vectors. Now we're going to make a claim, and this claim I hope to convince you what the effect of matrix multiplication. So the claim is, whenever we multiply a column vector by a matrix, that matrix transforms or changes the vector. So anytime we perform a matrix multiplication, that is, we take a matrix and we multiply that matrix, or we take a column vector and we multiply the column vector by a matrix, the result is that that column vector gets changed or gets transformed. And here's one example to motivate this statement or this claim. Let's take some matrix. I'm going to call this matrix A later on, but for now it has 0, 1, and 1, 0 for its entries. Now take our vector x bar and multiply this vector x bar by this matrix. Well, let's go back to our old school matrix multiplication, is that we take the first row of the matrix and we multiply that by the column. So that's going to be 0 times 1, that's going to be that gives us 0, and add to that 1 times 0. So it's 0 plus 0, so our first entry is 0, 0. It's 0. What about our second entry? Our second entry of the output column is going to be the second row of the matrix times the column vector. This is going to be 1 times 1 plus 0 times 0. That is 1 plus 0, and the outcome is 1. So the outcome, the resulting column, has 0 on its x coordinate and it has 1 on its y coordinate. Well, that looks exactly like what we've designated as y bar. So notice, we took a column vector x, we multiplied by some matrix, and look at what we end up with. It's something that's different from x bar. So I hope this convinces you that anytime we multiply a column vector by a matrix, effectively that column vector gets transformed. In summary, this matrix changed or transformed vector x to vector y. Now, let's do one more example to further motivate this idea. Suppose this time around we don't begin with vector x, but we begin with vector y. Over here I have given this matrix, same matrix as before, 0, 1, 1, 0. But now instead of having an x column here, in other words the x vector, we take this vector, the y bar vector. And let's again perform the matrix multiplication here. It's going to be this row times this column. So this 0 times 0 plus 1 times 1. What does this give us? The outcome of that is 1. So that gives us the first entry. What about the second entry of our resulting column? We're going to take this row again, multiply by that column. So we have 1 times 0, that's 0. Add to that 0 times 1, and 0 plus 0 is 0. So we get 0. But notice now, this vector here is nothing more than what we designated as x bar. So notice, we began with y bar, and by multiplying y bar with this matrix A, the outcome is x. Again, this matrix A has transformed the vector, the column vector y bar, to the column vector x bar. So I hope by this much you'll be able to agree with me that, loosely speaking, without taking care of all the algebraic demands, but loosely speaking, we can say, in general, a matrix R acts on a vector V and transforms it to another vector W, i.e. mathematically, or we could write it as this equation. So we take our vector V bar, we multiply with some matrix, and the outcome is we get another vector, different from the initial one. But now let's consider, take this this matrix, and this time consider what is the effect of this matrix on a vector like T bar. Let's go. So this is the question we have. We are interested in the effect of matrix A on a vector T bar. Well, let's test our question. Let's take our vector A, first row, multiply the column. What do we get here? It's 0 times 1, that's 0, plus 1 times 1. So 0 plus 1 gives us 1, so check. Now for the second entry, it's going to be this row times that column. So 1 times 1 gives us 1, add to that 0 times 1. So this basically is 1 plus 0. This means our entry here is 1. But this column is nothing more than T bar itself. So effectively what we began with is that we took this matrix and we took this column, this vector, and we multiplied by this matrix, and it gave us back the vector we started off with. And I have to highlight that the matrix we multiply T bar with, this matrix here, is not the identity matrix. Because remember, the identity matrix does not change anything it multiplies. It leaves it unchanged. But this matrix here is not the identity matrix. So the fact that it has kept this column unchanged is quite significant. Now, this is where we will begin to introduce the idea of eigenvectors. Any vector V bar which satisfies this equation is called an eigenvector of the matrix R, and lambda is known as the eigenvalue of matrix R. So now notice, this equation is very similar to what we had here. What makes V bar special is that whenever it's multiplied by this matrix R, it doesn't change to something else, but it reproduces itself, albeit with a multiple, but the point is it reemerges, V bar reemerges. That's what I think in German eigen means self. This V bar is a unique vector that when it's multiplied by this matrix, it reproduces itself. Another way of saying this is that eigenvectors always produce vectors that are collinear. In other words, this V bar is parallel to this thing here on the right. It produces something that is on the same line as itself. This is where the idea of eigenvectors comes from. It is a very unique property of these vectors that whenever they are multiplied by matrices, they seem to retain their structure, albeit with although maybe they might be rescaled, or maybe their direction reversed, but the point is they will always be collinear to their original column. I hope this much gives you a bit of a recap of how eigenvectors and values show up in mathematics. It's because in general, we expect this to happen, is that anytime you multiply a matrix with a column vector or a column vector with a matrix, the outcome we expect is some other vector W, different from what we began with, different from V. But when the outcome vector is the same as what we started off with, or is a multiple of what we started off with, that is a very special situation. Okay? From here on, we will therefore consider the eigenvalues and vectors, and in particular how they show up in differential equations.